Good morning. We're coming to you live from NASA's Kennedy Space Center here in beautiful Florida, where tomorrow we're going to be launching the Transiting Exoplanet Survey Satellite, better known as TESS. And it's going to be launching tomorrow at 6:32 p.m. Eastern Time here from Space Launch Complex 40 over at Cape Canaveral Air Force Station. So we're going to jump in and go right behind the scenes here, get a quick overview of a bunch of different things related to this mission, everything from the rocket to the spacecraft to the science it's going to be doing once it's up on orbit. And so we're going to jump right into it here without wasting any time. If you're following online, we're going to be looking for questions using the hashtag AskNASA, and we'll be taking those along with questions from folks here in the room. And so our first speaker, though, is the Vice President of Build and Flight Reliability from SpaceX, Hans Koenigsmann.
All right, thank you. Yeah, my job at SpaceX is making sure that the rocket goes the right way and launches satellites reliably and safely. That's what Build and Flight Reliability as a team overall does. Tomorrow evening, we will launch TESS at 6:32. Not quite a the sun's going to be down, so it's going to be really well visible, but not quite as well as it could be in the dark. But either way, you're going to get a great show here. Let's see. The rocket will fly for about 3 minutes and then separate the stages. The first stage will go and perform a landing on a drone ship, and I'm going to talk about that in a second. The second stage continues. We'll go into a parking orbit for a while, and then after 40 minutes in that parking orbit, we'll do a second burn and bring TESS out very close to the moon, deployed after the burn is over, and I guess we wait a couple of minutes after that. Going back to the first stage, we will land on a drone ship. The drone ship's name is, I think it's the Of Course I Still Love You. And I do have a short, brief introductory video that shows you a couple landings, just to get everybody excited about the landing too. Can we have that? And this one is one of my favorites. It has this high crosswind. You see how the rocket leans and then uprights in the last second. Looks very dynamic. And that's roughly how it's going to be looking tomorrow too. Land landings, we will not do a land landing this time. We do a drone ship landing because it's a softball landing on the rocket, basically. And this is landing zone 1. It's down south of us, and that's where we usually land when we go back to land. By today, we had 23 landings in total, and see if I get this right. I think 11 were on land, and the rest of them, 12 then, were on the drone ship. I think that's the last one in the video. I'm just going to hang out there. I think that's almost all I had. I just want to say this mission TESS is super important for us. It's a big science mission, and it connects. SpaceX has the goal to make mankind multiplanetary, and TESS looks for new planets, so to speak. So in some way, it connects the science back to what the goal of our company is. We do have to work a little bit on the propulsion technology, however, to get to those planets. And that's it, what I had.
All right, wonderful. We'll be taking questions here. If you have a question, raise your hand and wait for a microphone. And so we'll start down here in front.
Hans, even though you don't have Mr. Steven on this coast, will you be testing fairing recovery gear?
Yeah, we sort of do. We will have the same parachute, and the fairing will land softly, but it will land softly in the water because, as you pointed out, Mr. Stevens is over at the other coast, and we couldn't bring it over. We continue testing that part on the other coast.
All right. Other questions for Hans here about the rocket? Yeah.
Are there any special considerations for the launch due to the unusual orbit that TESS will be taking?
Let me think about this. I don't think so, frankly. I mean, there's a very brief launch window. It's not quite. It's almost an instantaneous launch window for that matter, basically. But you can shift a little bit. It changes every day by more than what is usual, but that's also not that unusual. And other than that, it looks somewhat similar to a geotransfer orbit from what you will see.
Next question.
This is a Block 4 Falcon 9.
Right.
Is there plans to reuse this for maybe a future
Yes.
CRS mission, maybe?
Yes. This one will be, well, I can't speak for NASA. We need to discuss this after the landing, obviously, after refurbishment. But this one is planned right now for the next CS mission.
All right, next question's over here.
So you were talking about refurbishment. About how long does it take to refurbish?
I don't really know exactly. It's a couple of weeks, and I know we have enough time between now and the CS launch. That's and I do have to remember now when the CS launch was. I think it was in June. So it's a couple of weeks. Zoe.
All right, one more question down front here.
Yes, hi. Will you purposely deorbit the second stage?
Will we put what?
Will you purposely deorbit stage 2 for this mission?
Oh, that's actually a good point. We will not deorbit the second stage, but we will basically kick it out. We will do a third burn, and there will be a disposal burn to hyperbolic, basically. So it's that's actually one thing that is very, very different than usual. Thank you. Good question.
All right, then, just a reminder for folks who are viewing online, if you want to ask a question, you're welcome to use the hashtag AskNASA, and we'll be looking for those questions throughout the broadcast today. Do we have any other questions in the room here for Hans about the rocket? All right, then. Well, we look forward to seeing a successful launch tomorrow at 6:32 p.m., so thank you very much.
Oh, thank you.
Definitely. Thanks a lot. All right. Up next here, we're going to go and dive a little bit behind the big theme of the day today, and that's exoplanets. So we're going to talk about how we're searching for planets that are orbiting around other stars out there. So to jump in and talk about this a little bit with us is Martin Still, who is the program scientist for TESS, as well as Jesse Christensen, who's a staff scientist with the Exoplanet Science Institute. So take it away.
Good morning, everyone. NASA astrophysics exploration has several overarching themes. One is, what is our universe made of, and how does it change over time? Another is, where did we come from, and where are we going? And another is, are we alone? Is there life elsewhere in the universe? Exoplanets, these are planets that orbit other stars to our own sun, are fundamental and important to all of these overarching themes. 25 years ago, when we looked up at individual stars in the sky, we always wondered whether there would be planets around that star. 25 years on today, when we look up at individual stars in the sky, our question is, well, our thought is, it would be really strange if there were no planets around that star. That's how far we have come over recent years. However, we have a fundamental problem ahead of us, which is why we are launching the TESS mission. Many, many of the planets that we have discovered up until now are a long way away, and so they're much more difficult to characterize. NASA has sort of a three-pronged approach to exoplanet research. One is detection. Where are the planets? Where should we look for them? The other is characterization. What do they look like? Do they have atmospheres, solid surfaces? What are the constituents of that atmosphere? And then finally, can we find any evidence for biosignatures, an opportunity for life to take hold on those worlds? Right now, we're still in discovery mode. And to get to the characterization mode, we need to find those planets which are nearby and considerably more easy to characterize than the yield of planets we have so far. So Jesse, I know you as one of the scientific leaders of the Kepler mission. I also know you as an archivist of NASA's exoplanet archive. What scientific foundations do we currently have that we are going to use TESS to build upon?
Thanks, Martin. So as Martin said, less than 30 years ago, we knew of 0 planets outside of our solar system. Today, we know of thousands. So I'm just going to give you a very brief summary of some of the highlights of things we've found to set the stage for TESS. If I can have my first graphic. So what I'm showing here are the planets we knew before 2010, only 8 years ago, where we knew their size. On the vertical axis, I'm showing the size of the planet relative to Earth, so small planets are at the bottom and big planets are at the top. On the horizontal axis, I'm showing the period of that planet, its year, how long it takes to orbit the star. So short period planets are on the left and long period planets are on the right. The 4 magenta squares are the inner solar system planets in our solar system: Mercury, Venus, Earth, and Mars. The circles are the exoplanets that we had found. So that big clump of blue planets up at the top, these are gas giant planets like Jupiter that orbit their star only every few days, unlike our Jupiter, which takes 12 years. So these planets are thousands of degrees, and we call them hot Jupiters because we're not very imaginative. But they're the easiest planets to find because they're big. So we were able to detect those from the ground. And for the last 2 decades, they've been teaching us a lot about the structure and composition of hot gas giant atmospheres. In 2009, NASA launched the Kepler mission, which really changed the landscape. If I can have my next graphic. You can see how this plot's really filled in from the hot gas giant planets down to the cool rocky planets like Earth. First, let's talk about the color scheme. The blue circles are systems where we've only identified one planet. So these hot Jupiters, turns out they're lonely. They're usually found on their own. But in the last few years, we've found more and more larger systems with more and more planets. So 5, 6, 7 planets in the beautiful animation of TRAPPIST that was showing while Martin was talking. And recently, Kepler 90 was found to have 8 planets, just like our solar system. We haven't yet found our solar system's true twin, but what's really fascinating is the variety of the types of systems we've found so far. One last result I wanted to highlight from the Kepler mission is that most of the planets we found, the bulk of them, are between the size of Earth, which is at 1 on this vertical axis, and Neptune, which is at 4. The reason that's interesting is there's nothing in our solar system between the size of Earth and Neptune. So this is exciting new territory, and scientists love that. So we don't know what these are, whether they're scaled up rocks like the Earth, or scaled down ice giants like Neptune, or something we don't have in our solar system, like water worlds. Lots of people are working on this right now, but what we really need is more planets in this size range where we can measure the mass. Once you have the size and the mass, then you can start talking about density, and that's how you tell the rocky planets apart from the icy planets apart from the gassy planets. So as Martin said, that's why we need a mission like TESS to find these planets that we can measure the masses of. Thank you.
All right, so we'll take some questions. Again, if you're following along online at home, you can use the hashtag AskNASA to ask your questions. So first question is going to be here in third row.
Morning, Christian Wong with Hawaii Science and Tech Museum. My question is for you, Jesse. So being that the ultimate goal here is to answer the question, are we alone? The question I wanted to know is that since TESS is going to be focusing a lot on the red dwarf systems, and you have differences there, as well as the planet probably being tidally locked to its star, what type of differences do your astrobiologists think would be with the Earth, with the life on there, and how does that affect the type of signatures you're looking for the biosignatures?
Sure. That's a great question, and that's something that a lot of people are working on very actively right now. What does the habitable zone look like around an M dwarf, which can be putting out thousands of times more UV radiation than our Earth? That's a very active area of discussion, and I don't have an answer for you right now, just to say lots of people are trying to find the exact answer to that question.
All right, next question. We'll go down in front, and then I see one here and one over there. So,
How are you going to process all of the data that you receive from TESS?
Oh, that's a great question. One of the big differences between Kepler and TESS is the sheer amount of volume, the volume of data that's going to be coming down. I don't know if we have someone who can particularly answer the processing question. Maybe Natalia wants to take that one. One of our latest speakers will give you more information about the processing. But yes, it's a big problem. We've got an order of magnitude or 2 times more data coming down.
Sure. So the short answer is that when the data is downlinked, I'll stand up. When the data is downlinked to the Payload Operations Center at MIT, it is sent to NASA Ames for analysis. And when it comes back, that's when scientists at MIT who are very experienced in this actually go through and by eye identify in the light curves dips that look like they might be planets. And Zach will talk more about what those light curves will look like.
Could also add one more thing to that, is that the data themselves will be made public very rapidly. They'll be put into an archive. Once we're in smooth operation, within a few months of that data being collected. So there's a very strong chance that people from the public will actually find some of these planets before people from the scientific community do. It's going to be a lot of fun for everybody.
All right, next question's down in front here, and then I see one in the back. Are there others?
Good morning. You'll never see a transiting planet that's perpendicular to us. You're very lucky to see a few degrees in our plane. Do you have an estimate of the ratio of ones we'll never observe compared to ones we can?
Yes, so that's something that's a fairly straightforward geometric probability that you can work out, which has to do with the ratio of the size of the planet to the distance from the star. So for something like the Earth, it's about a 5% chance of transiting. And for something like Jupiter, it's more like, if you had a Jupiter at a few days, like these hot Jupiters, it's more like 10%. So when we're working out population statistics with Kepler, we correct for that fact. We say, okay, these are the ones we see, which means we're missing 90% or 95% or 99%.
Sorry, as a follow-on, do you have any estimates of how often the plane of exoplanets are matching the plane of the ecliptic, or are they random?
So the exoplanet systems we see on the sky are isotropically organized. They're random on the sky. But they're very well lined up with each other. Within that plane, they're very flat, which I thought was where your question was going. Like our solar system is flat, and we think that other solar systems are flat as well.
All right, I saw there was a question in the back here.
Hi, good morning. I just wanted to ask, why the decision to scan each sector for only 27 days? I know you're going to scan, 85% of the solar system, but why the decision for 27 days for each sector?
That might be a better question for someone who's handling how we do the observations, Tom.
We can get
It's
to
the
that
lunar
when
orbit.
Tom comes up and so on here in the next couple of segments.
It
so.
has to do with the lunar orbit, basically.
Yeah, we'll touch on that a little bit here in a minute. Next question here.
Yeah, you said you were looking to categorize, and you talked about categorizing by mass. Are there other ways you wish to categorize, and why would you want to categorize them that way?
Oh, sure. What an excellent question. So one of the things we want to do is look at the atmospheres of these planets. We have some planets now that we're looking at the atmospheres from, and for instance, are they cloudy, are they hazy, are they clear? These are all really interesting atmospheric questions we want to ask, and building up populations of these. What makes a planet have a cloudy atmosphere? What makes it have a clear atmosphere? That's kind of the next step that we'll be probing with something like the James Webb Telescope, which will launch in the next year or two.
All right, any other questions here? All right, well, good luck, and I hope that you get an incredible data set that'll let you just keep finding more and more out there, so more and more exoplanets.
Thank you.
Thank you very much. All right, we're going to jump into talking about and looking at, TESS as a mission and so on, and how it's a little different than one of the missions you just heard a little bit about called Kepler. And so to do that, we're going to have Tom Barkley, who is the TESS scientist at NASA's Goddard Space Flight Center, and we're going to have Jen Burt, who is the Torres postdoctoral fellow from MIT, join us to tell us a little bit about TESS and how it's different.
Fantastic. Good morning. Isn't this exciting? We've been planning TESS of the whole mission for several years now, so this is really the culmination of an enormous amount of work to get this thing built and get ready to go into space. So what is TESS? It's a spacecraft that will be launched. It's about the size of a fridge. We're debating during our practice whether it's a washing machine or a fridge size, but maybe somewhere in between. But it's a small fridge. It's an appliance-sized spacecraft, so it's quite small. And it's going to be going into, as mentioned before, pretty special orbit. So it will take off from Kennedy, Cape Canaveral, tomorrow. It'll then go in through several orbits, as discussed. But what's very exciting is it goes really relatively close to the moon, and it gets a really good kick from the moon. The moon's going to incline the orbit to our own Earth-Moon plane, and that's going to put it into its final orbit. The final orbit's an orbit of about 2 weeks. The spacecraft's going to orbit the Earth every 2 weeks.
Do you want to explain, though, what you mean by incline the orbit?
Yeah. So of course. The moon and the Earth orbit each other. They're flat. It's about the same plane as the sun. Our own whole solar system's in about the same plane. TESS is going to go around not in that plane. It's going to go around like this rather than flat. So whilst it's going around, it's going to spend most of its time fairly far from the Earth and then come in relatively close to the Earth to download all its data. So why do we do this? One of the questions was, why do we look for 27 days? 27 days is a nice balance. You can find a whole bunch of planets, but at the poles, you can look for a lot longer than 27 days. You actually look for about a year at the poles and 27 days at the closest to the ecliptic. And if we want to show them a movie now, this is showing you how we observe. Here's the field of view. So each of these tracks here is actually about the size of, if you were looking at this stage behind me, this is about the right size of kind of a panorama image using 4 cameras. And each of these cameras is about 500,000 times bigger than the field of view of Hubble. These are really huge cameras we're looking at. And then we're going to move them around, looking at the sky, trying to find planets. Now, you'll remember Kepler. Kepler was NASA's first dedicated exoplanet mission. How is it different? Jen here is going to talk about some of the differences here.
Yeah, thanks. Yeah, so Tess and the scientists who are working with her are in this really fortunate position where we get to stand on the shoulders of an amazing mission like Kepler. Now, the main difference with Tess, as Martin mentioned earlier, is this desire to look at our closest and brightest stars, kind of our stellar neighbors, if you will. So if we can roll my first video, please. This is going to show you, starting off, the Kepler field of view, what we looked at for 4 years. There we go. So that's the constellation of Cygnus, and then the cross that shows up here is what Kepler stared at. And then on top of that, that's one of the TESS cameras. It's about the size of Orion on the night sky. Now, each 27-day sector is comprised of 4 cameras, making this vertical strip. And then what TESS is going to do is tile those strips, starting first in the southern hemisphere, as you see moving across the bottom of the screen. There we go. And then it'll switch to the north after its first year. And over those first 2 years, its primary mission, it'll cover 85% of the sky. Now, by looking at such a large section of the sky, this kind of stellar real estate, we open up the ability to cherry pick the best stars for doing follow-up science. On average, the stars that TESS observes will be 30 to 100 times brighter and 10 times closer than the stars that Kepler focused on. Now, what that means in terms of detecting planets is that our planetary census is going to move in. If we can pull up my second video, but just leave it on the first screen for a second. Perfect. So this is going to be an animation that will show you, zooming out, the planets that we found already. The ones found by Kepler will show up in blue. Planets found by other missions will show up in gray. And then planets that we think TESS is going to find using a variety of very well-designed simulations will show up in orange. So what's happening here is we're looking down on the plane of our solar system. And then if we can start the video, please. We're going to zoom out. So that first circle is 3 light years. Next one is 10. You can see that within 30 or so light years, we already have some orange points. And as we zoom out further and further, you'll see that the screen is just covered in these orange dots, these predicted TESS planets. And eventually we see the contributions of Kepler and other missions come in, kind of stretching much further at the 100 or 1,000 light year level. But that central area that TESS is dedicating to is really where I think the majority of great exoplanet science and characterization is going to happen over the next couple decades. Because the planets that TESS finds will be orbiting stars bright enough to use things like ground-based telescopes to do radial velocity work, which is how we get masses of planets. When we combine those masses with the radii that TESS provides, we can start talking about things like planetary composition and what they're made out of, like Jesse mentioned earlier. And then for the very best and brightest and most promising candidates, future missions like the James Webb Space Telescope, which should launch in 2020, will be able to stare at those planets and peer into their atmospheres, looking for evidence of the atoms and molecules that we think might be crucial for letting life develop on those worlds. So TESS is really the next step in all sorts of goals for NASA, and we're really excited to see what science comes out of it.
All right, wonderful. So who's got questions about TESS and how it's a little different than what we've had in the past? Sure.
Always got something. So TESS is relatively small in terms of observatories. Were you budget constrained, spacecraft bus constrained, or what were the boundaries?
I mean, NASA has several sizes of missions of which it flies, from the very massive flagship missions all the way down to CubeSats. And TESS happens to be a medium-sized Explorer mission, so we have a budget cap of which we build to, and we realized we could do some fantastic science, some groundbreaking science, while still fitting into a modest-sized budget for the operations.
All right, question in the second row over here.
Good morning. So I'm wondering what's different about these cameras? What makes them so extraordinary for this particular mission?
So the big difference, as we've shown in these graphics, is because of the field of view, is the fact that the TESS cameras are designed to cover such a large portion of the sky at once. Because when we designed Kepler, the idea was just to make sure that planets were, as common as we hoped, and that there were really enough of them in the night sky to justify then doing this broad survey approach to really covering the whole sky and being able to count on the fact that even if we look at a sector for only 27 days, there are hundreds and thousands of especially small planets that we'll be able to find. So yeah, the big thing is just being able to open up the sky and cover 85% of it in only 2 years. That's kind of a big deal.
Wonderful. We had another question down in the front row here.
How is TESS powered, and how does that differ from Kepler? I know Kepler's going to run out of gas fairly soon.
Yeah, so TESS and Kepler are powered by the sun. They both have solar panels. One of the key moments in the coming days tomorrow will be when the solar panels unroll, and we're anticipating that successfully happen. Kepler's is coming to an end at some point in the next year or so, because it's running out of something called hydrazine. But that is because Kepler's not operating in a standard way. It's not operating in the way it was designed to. The engineers came up with this fantastic method to keep Kepler going, but it uses a resource that people hadn't expected to be running out. So the fact that it's gone on and continues to go on and do this groundbreaking science as long as it has is fabulous. TESS also has hydrazine in it. TESS will do burns. Earlier we mentioned some of these burns to get it into its final science orbit. But once it's in that orbit, it shouldn't need to do too much fuel burns to keep it in that orbit, because it's fairly stable.
Yeah. So that lunar orbit that we were talking about earlier, where we're in this nice 2-to-1 resonance. So for every 2 times that TESS goes around the Earth, the moon goes around once. That ratio actually keeps TESS very stable. We think on the order of 20 years or so. So every 2 weeks, the moon helps to kind of nudge TESS back to where it should be and keep everything aligned so that we don't have to worry about it kind of floating off into looking at the wrong part of the sky.
Crash with a Tesla?
Yeah, we should track where that thing's going, but I'm pretty sure we're okay.
All right, other questions? Yeah, second row here.
About how long after launch is it going to be till you guys start your actual mission, like after you verify everything's good?
So I'm pretty sure, and Natalia can correct me on this, that when launch happens tomorrow, is somewhere in June we start getting data back. Is that right? July. Okay, so somewhere in July we start getting data back, and we do a little bit of commissioning and some test runs just to make sure all the cameras are working correctly. And then somewhere in August, I think the actual science data starts coming down that we can, really open up the exoplanet world with.
Yeah, for the scientists and the engineers working on the cameras, the exciting and terrifying time comes, I think, about 2 weeks in, when the cameras get turned on for the first time, turned on one by one, and anticipation's high that these images will be beautiful right from the start.
Yeah.
All right, we're gonna go down front here.
Can you explain a bit more what the data analysis will look like as it comes in?
Sure. So Zach's going to talk about exactly what a light curve from TESS will look like when he speaks later today. But the basic idea is that the data comes down, it gets sent to NASA and MIT, and then the teams there start pouring through it looking for evidence of these planets. Now, because the TESS cameras are so big, that also means the pixels are quite large. So in any given pixel of a camera, there might be more than one star. So while we might see transits, we might see these signals that we think are exoplanets, there's a lot of careful checking and vetting that needs to happen. And so that'll be a big part of the TESS mission, actually, is making sure that the signals we see are actually due to exoplanets and not due to additional stars or kind of info coming in from another part of the camera. So that's going to be, I think, the biggest hurdle. But from there, once we find candidates, they get released to the community. And TESS is this great system where the data goes public immediately. The planets we think we find go public as soon as we have decided they're trustworthy. And then anyone around the world can follow up those planets and try to learn about them in whatever way they think best.
All right, last question. We'll go down front here.
Hi. What happens to TESS after this?
After the first 2 years? Yeah, so the primary mission is the first 2 years, and then hopefully there's enough demand from the community and support from astronomers around the world that think TESS is a great idea, and it will keep on keeping on for those other 18 years that we think the orbit's stable for. That's what we're all hoping, at least.
Yeah, I look forward to a long and exciting era of discovery from TESS. but we'll see.
All right. Thank you all very much.
Thank you.
All right. So now we get to do a little bit of show and tell, and so this is going to be exciting. So we're going to look at how the data gets gathered and how we identify exactly what are these exoplanets out there. And so with that, we've got Zach Berta Thompson here, who is an assistant professor with the University of Colorado Boulder.
All right, thank you. Yeah, so I wanted to take the chance to try to give a sense of like what exactly is TESS doing, what are the observations we're getting, how do those tell us that there are planets there. And so to do that, we need to back up a little bit, and we need to talk about the distance between stars and why it is hard to find planets. So let's imagine shrinking down the entire universe so that we can fit the sun into this room. The sun will be the size of this light bulb, which will hopefully turn on. Great. And so if this is the sun, we of course know that there are billions of other stars out there in the Milky Way galaxy. So we can ask, where would the closest star be if this is our sun? The closest star would be a few thousand kilometers away from us right now, like in Colorado, if we're here in Florida. So if we want to find a tiny little planet that's going to be pretty faint, I've made this one particularly big so that we can see it by a factor of 10, maybe 100. It's going to be really, really hard to see this planet next to this very bright star from halfway across the country, right? So that's a hard thing. That's not what TESS is going to be doing. What we're going to do with TESS is we're going to take advantage of those few random systems that happen to be lined up so that as planets are orbiting around their star, they pass in front of the star as seen from Earth. So there's this little transit. That's where the transit in transiting exoplanet survey satellite comes from. This transit of the planet passing in front of the star. And we still don't get to take a picture of this planet in front of the star, its little silhouette. But we can look for the brightness of this star dimming when the planet is passing in front of it and blocking some of its light. So to be able to find a planet, all we would need to do would be able to measure the brightness of a star very carefully. If we could bring up my first slide here, I can emphasize that this is something that astronomers have been pretty good at for a long time now. For example, Henrietta Leavitt, my scientific hero, she's the one on the left with the magnifying glass there, working about a century ago, made repeated brightness measurements of a particular kind of variable star, Cepheid variables, and used those variable stars to figure out how to measure their intrinsic brightness. Other astronomers then went out, used her work, used those stars to measure the distance to other galaxies, determine the fact that the universe is expanding, and learn the age of the universe, all from these brightness measurements of stars. And so she had to do this work. Actually, we could bring the next slide up again. She had to do this work with photographic plates. So these are glass plates, stars imprinted on them from a telescope. And she had a little fly swatter with reference stars that she would compare to by eye to make these brightness measurements. And so this is hard work, and she made beautiful measurements out of these data. TESS, like the Kepler mission before it, is building on this legacy of stellar photometry, of measuring the brightness of stars. Of course, TESS is using extremely sensitive CCD cameras instead of photographic plates. TESS can observe millions of stars at once. And TESS can measure the brightness of those stars to a precision that is much better than anything we could ever hope to do from the ground. And so TESS is really, you can think of TESS as taking a movie of the sky, essentially, over this really big field of view. If we can bring up the next animation, I want to show you a little snippet of that movie. So on the left here, I've pulled out just a few pixels of some simulated data. And this is, let's see, the pixels you're seeing there has a few stars in there. That is about 1/100,000th of all of the pixels that TESS will have at any one time. And you can see in the center, there's one little star there that's winking out occasionally. And the reason that star is winking out is that we've imagined that there is an impossibly big planet passing in front of it. So a planet that is basically blocking out all of the light of the star. So its brightness drops to 0. And you can see that in the light curve of this brightness as a function of time. Brightness going from 100% all the way down to 0. Of course, as I said, real planets are smaller than this. They won't block all of a star's light. So if we go to the next animation, I've replaced that enormous planet with a, can we go on to the next, please? Ah, perfect, there we go. And notice on here, the scale has shifted. So now we're seeing a tiny little dip in the brightness of the star that is 1/4%. So this is actually an Earth-sized planet transiting a fairly small star, so a star that's much smaller than the sun. But if you look at the movie, you can't see anything happening at all. You don't see that star in the center winking out. That's because it's a very, very tiny change in the brightness that we're looking for when these small planets transit in front of their stars. And so TESS, because it has such exquisite precision, has the ability to measure that transit and tell that there's a planet there. So with TESS, we'll be able to find planets through this technique. We can also, as you can imagine, figure out the size of the planet because we know the fraction of starlight that the planet blocks, right? But we can also get the orbital period. We can tell how frequently does the planet pass in front of the star. And if you have an orbital period, you can make the beautiful demographic plots that Jesse showed us earlier. You can also figure out how far away the planet is from its star by the laws of gravity. And so therefore, how much heat that planet receives from its star, and therefore, roughly what temperature that planet is. And so that's how we can tell, even with TESS data alone, roughly is this planet way too hot for liquid water? Is it too cold for liquid water? Is it just about right for liquid water? So there's a lot that you can learn from TESS data, even just looking at single points of light. So I'll leave it there and take any questions.
Wonderful. Who's got questions about TESS data? All right, we'll go here.
Hi, how do you ensure that the dip in brightness you're looking at is from an actual planet and not like a sunspot or something that's with the rotation of the sun, or the star, rather?
Yeah, that's a fantastic question. If we could actually bring up my last animation again. Exoplanet astronomers aren't the only astronomers out there, right? There are astronomers that are interested in everything. There are astronomers who are really interested in sunspots, on star spots, on other stars. And so TESS, on one hand, is going to get a lot of really beautiful light curves of star spots on stars. And so we'll be able to teach us about the physics of stars through those. But if you look at this light curve here, a transiting planet has a very characteristic dip. It's a very tiny fraction of the planet's orbit where the planet is actually in front of the star as seen from you. Most of the rest of the orbit, the star just looks pretty ordinary. And so you're looking for just this boxy little dip in the brightness of the star. A star spot will be rotating with the, I wish I had a worse light bulb here. A star spot will be rotating on the surface of the star, so it'll spend like roughly half of the rotation period of the star in view. And so you'll see this sort of smoother modulation in the brightness of the star overall.
All right, just a reminder, if you're watching online at home, we're taking your questions using the hashtag AskNASA. Feel free to send those in, and we'll get to those here in the room. So other questions about the data that TESS is going to be collecting here?
And what is the smallest dip in brightness that would still be statistically significant for TESS?
So for that dip that I was showing, there was about 0.25% in brightness. Our sensitivity will depend on the brightness of the star that we are looking at. But for very bright targets, we'll be able to detect dips that are, let's see, so smaller than, down at about the level of 0.01%, so 100 parts per million. So those are the smaller transit that you can detect, the smaller planet that you can find. And so though astronomers, myself included, have been looking at many of these nearby stars, looking for planets around them, a lot of us have been doing that from the ground. And so we've only been able to see dips that are like 1% deep. And so the real boon from TESS is being able to find these much, much smaller dips to be able to find much, much smaller planets, which we know, thanks to Kepler, are enormously more abundant than the large planets.
All right, last question we're going to pull from Ask NASA here.
I have a question online from Lisa Marie. What factors will allow the optional 18-year mission extension?
So the spacecraft itself should continue to work beautifully if everything goes according to plan. And so really that will be continued funding to be able to support the scientists who are making the operations continue, analyzing the data, running the spacecraft. And so I think this is a mission that an extended mission for TESS could be enormously beneficial to the community.
All right, wonderful. Thank you very much for showing us the transit method here and how the data is going to get collected. All right, now we're going to jump into kind of what we hope to discover. So you've seen like some of what the data is going to look like and everything. And so joining us here is Elisa Quintana. She's the TESS scientist at NASA's Goddard Space Flight Center, and she's going to tell us a little bit about, what do we hope to discover here. So take it away.
Hi, everyone. Thank you for coming. And can I have the first slide, please? So to date, we now know of thousands of exoplanets. The vast majority of them were found by the Kepler mission. Here you can see a wide variety of exoplanets, and this is just an artist's illustration. We're not quite there yet to take nice, pretty pictures of this. But what we do know is that we found such a wide diversity. So we found planets as small as Mercury. We found planets Earth-sized and even bigger than Jupiter. We've also found planets orbiting all types of stars. So we know of planets that orbit sun-like stars. We know of planetary systems that orbit stars that are even as small as the planet Jupiter. And so lots of small, cool stars have planets. We also know that planets even orbit red giants. And so that's sort of where the sun's going to evolve in one day. And so TESS is going to find thousands of more planets, and hundreds of those are going to be at least twice the size of Earth and smaller. And so we're really going to have a huge amount of exoplanets to study. The beauty of TESS is that these thousands of new planets TESS is finding are going to be orbiting the nearest brightest stars. And so these are stars that are 30 to 100 times as bright as the Kepler stars. And the reason that's important is because astronomers all over the world, everyone from amateur astronomers to people at Keck, can point at these stars and try to learn more about these planets. And if they orbit bright stars, you can start to try to measure their masses. The TESS mission, through transits, just like the Kepler mission, gives you the planet's size relative to the star. And it gives you the orbit very precisely. And so if you combine that with all of the mass measurements, that gives you the density. And so Kepler has this this huge data set of exoplanets, and TESS is going to give us sort of another valuable set where we know much more about them. And so the TESS planets are really going to be these touchstone planets that are going to be studied by current and future missions for a really long time. Next slide, please. And so here's another illustration of some of the space missions from NASA. Shown from the left to right is the Spitzer Space Telescope. TESS is next. Hubble Space Telescope is in the middle. James Webb, and on the far right is the Kepler mission. And so all of these have a wide variety of astrophysics they do, but also have an exoplanet component. And so so Kepler was very revolutionary. We didn't even know if Earth-sized planets existed before Kepler launched. And Kepler taught us that Earths are common, and as Jesse talked about earlier, these planets that are in between Earth and Neptune are actually the most abundant. We also learned that Jupiter-sized planets might even be rare. And so Kepler really basically told us that we didn't know much, and everything that it discovered was a surprise. And so we might have the same experience with TESS. We'll have to see. There's still Spitzer and the Hubble Space Telescope are still going to be in operation, and they have been really successful in observing a lot of the larger planets that ground-based and the Kepler Space Telescope found. But we really pushed the limits to what Hubble and Spitzer have been able to do. We are building the James Webb Space Telescope, which will launch in a few years, and that's going to allow us to even probe the atmospheres of much smaller planets. And so we have this nice sort of plan to go from do planets even exist to what types of atmospheres are there, and what's the distribution of the properties of all of these exoplanets. And so this is all really exciting. Next slide, please. And so here I just showed an image of the Earth taken from the space station. And this is just to illustrate how small the Earth's atmosphere actually is. And so the future of exoplanets really is trying to learn more about what they're composed of. And so the first exoplanet found was in 1995 around a sun-like star. And ever since then, the field of exoplanets has just rapidly progressed. And the first decade or so was all about detection, like all these single planetary systems we found. Kepler really revolutionized the field, and and gave us a lot of exoplanets so we could do demographics and learn about populations and how common are Earth-sized planets. The future is really characterization. And this is what TESS is going to provide. TESS is going to provide a catalog of lots and lots of planets where we can start to take these next steps. The inset shows a family portrait of some of the solar system planets taken by Voyager. And so these were images taken in the early 90s when Voyager was pointed back to take pictures of the Earth. So in the top middle section is the Earth and the famous pale blue dot planet. And this really changed our perspective of, our place in the universe. And so one day we might be able to know a lot about exoplanet atmospheres, and we might even be able to detect actual planets and direct imaging and actual image planets such as those in our solar system. And so this is a really great time to live. These planets were, excuse me, these photos were taken in the early 90s, around this first time that the exoplanets were being discovered. And so we really live in this nice time where we're finally able to answer a lot of these questions that people have been wondering for a long time.
Wonderful, wonderful. Thank you for that really great overview. We've got time for just a couple of quick questions here. So who's got questions about what TESS is going to discover? So down front here.
What information will you learn from TESS that was unavailable from missions like Kepler?
So TESS has a very similar method as Kepler. The transit method gives you the planet size very precisely. TESS is really going to find new planets that we can take the next step and study for. So it's not going, TESS itself is not going to provide any more features or parameters of exoplanets than Kepler did. What it is going to do is find which of our nearest stellar neighbors has transiting planets. And we'll be able to, we might even find planets that orbit stars that we can even see with the naked eye. So in the next few years, we might even be able to walk outside and point at a star and go and know that it has a planet. And so this is the future. We need to find planets that are closer to us to where we can take the next step.
All right, we've got another question, last question in the back row there. Wait for the mic.
Concerning imagery, if a pixel is as big as a baseball, how big is each individual image as far as size-wise, as far as data-wise, and how are you able to transmit all that information when you're making a quick loop around the Earth, in short distance? How is all that accomplished, and what are the sizes of those? I just find that very interesting.
Yeah, certainly. So TESS is going to collect a lot more data. It has each camera is a 24 degree, covers a 24 degree patch on the sky. So the 4 cameras lined up will be 96 degrees by 24 degrees. And those are going to stare at a patch of sky for the 28 days. And in addition to getting postage stamps every 2 minutes, it's going to download the full images of each sector every 30 minutes for as long as they're observed. So it's a much more larger volume of data that we're going to be doing. I know that in TESS's orbit, as Tom was saying, it's going to spend most of its time far away because it's a highly elliptical orbit. And when it comes down to Earth, it'll transmit the data. As far as data volume, I believe Natalia could probably answer that after when she talks about the spacecraft.
Wonderful. That's actually a great segue. Thank you very much here for joining us and telling us about what we're expecting to sign.
Thank you.
Wonderful then. All right, so we've talked all about the science it's going to do. We've talked a little bit about the rocket and everything, and how it's a little different from some of the stuff that's happened already with exoplanets out there. And so we're going to round out today's show with talking about the spacecraft itself, how it was built and assembled and everything else. And so here to join us today is Natalia Guerrero. She is a researcher on the TESS mission at MIT, and Robert Lockwood, who is the TESS spacecraft program manager for Orbital ATK.
Hi, everyone. So let's get the graphics up on the screen. The first graphic I have is just to show you all the different components that go into TESS. So TESS was a joint effort between MIT Lincoln Lab, and Orbital ATK. So I'll be talking primarily about the TESS cameras, which were developed at Lincoln Labs and tested at MIT, and I was part of the camera testing team. And and so Robert will also be talking about the things that Orbital contributed.
That's right. I'll be mentioning all the details, the nuts and bolts, and I always like hearing scientists describe the engineering details, but I'll actually be able to give you the exact details of your questions later.
Yeah, so let's go to the next slide, which is a cross-section of one of the TESS cameras. The cameras have 7 optical elements. These are 7 lenses that focus the light coming in from stars onto the CCDs. You can see the CCDs after that last flat optical element. And those are the charge coupled devices. That's an acronym. But these are extremely sensitive camera sensors. They're much bigger than, for example, the camera sensor on your iPhone or your cell phone. And these were developed at Lincoln Lab and tested at MIT. They can see in a bandpass of about 600 to 1,000 nanometers, or between the greenish to the very red part of the optical spectrum. So let's go to the next slide. The field of view, as many of the previous speakers have talked about, is really very large. So to give you an idea of what you can see in 24 degrees by 24 degrees, that's that blue square on the furthest right. That is the constellation Orion can fit comfortably into one of the TESS cameras. And so with one of the TESS cameras. And so you can see when you zoom into a 1 degree by 1 degree square, you have this very fine-grained view of the whole sky. Let's go to the next slide. So the cameras were tested at MIT. Here you can see one of the cameras getting fitted into the testing harness that holds it into place within the vacuum chamber where it was tested. You can see the black background, so that was a thermal coating. Let's go to the next slide. These are what we called, these were the vacuum chambers. We called them dragon chambers among the testing team. They were a larger size than the chambers used to test just the optical sensors, the CCDs, which were called the pup and pony chambers. So we thought a dragon was a size up. And I think this chamber was actually Norberto. We named them after different dragons in pop culture. And you can see the green eye of TESS winking at you there. That is the optical coating on the first lens in the array, and a technician working on getting that camera into the vacuum chamber. We had the chambers at minus 75 degrees Celsius and at vacuum, just like they'll be in space. So let's go to the next slide. And so now we're getting into more of the integration. Once the cameras had completed testing at MIT, we sent them, and the lens hoods, which is that black cone you see, was integrated onto the cameras, and these block outside light from getting into the optics. And then we started integrating these onto the camera plate, which is the next slide. Let's go to that. And so I'll hand it over to Robert to talk about that.
Yeah, so this is the capable team from MIT Lincoln Laboratory in our processing facility in Dulles, Virginia. They're integrating the 4 cameras into the camera plate. They actually don't work that quickly. This is a time-lapse photograph, so they actually set it into its camera plate very carefully. After this integration effort, we took the entire integrated spacecraft and instrument, turning it into an observatory, taking it through a whole set of environmental tests that simulate both the environment that it'll see in the launch vehicle, so-called shake, and the hots and colds of being in outer space, the so-called bake. So shake and bake it, get it ready for launch. We have, if you can bring up my slide, my first slide. This is a picture of the fully assembled observatory in our facility in Dulles. It has, there we go. I wanted to give a big shout out to these 2 very important people to me. That's my environmental and test manager, Mike Whalen, behind the vehicle, and my lead systems engineer, Sean Dreyer. I especially want to mention Sean because his parents are watching this social media presentation right now. So that's the fully assembled observatory. You can see the 4 cameras sitting there on the top in their little dog collar. That That's a sunshade that keeps light out off of the cameras, thermal protection, so they stay nice and cold at that minus 75 degrees. And then you see the 2 solar array panels deployed, and there is a high gain antenna for downlinking all of that volume of data when we come around near the Earth for downloading all the science data. So one of the questions earlier was how long was that? It's about a 5-hour pass to the Deep Space Network. We'll spin the spacecraft around and download something like 19 gigabytes of data down in that 5 hours. Then we'll just reorient and look at the stars during that entire 2-week orbit.
So let's go to the next graphic. I have a couple more of just the additional pictures of integration, which was very exciting.
Yep.
So if you want to go ahead with this one.
Sure, I'll talk about this one. Again, this is the crew doing their various checkouts. We take the entire observatory and we place it inside a clean tent. The lenses on the cameras want to stay nice and clean so they have unobstructed views of stars. So you can see everybody's in the so-called bunny suits, the head-to-toe coverings to keep all the contamination off. The biggest source of contamination is people, skin and hair, so you keep them covered up. And they take it through a whole series of functional tests in our environmental test facility in Dulles, and it's all checked out. We eventually move it down here to Kennedy. We did that in February, took it through another set of tests to make sure it was ready for launch, integrated it to the launch vehicle a week ago, and it's now sitting quietly. She is now sitting quietly over at the hangar at Space Launch Complex 40.
I think we actually have a picture of the encapsulation, or the encapsulated TESS as well. But yeah, there was also like the solar panel deploys that we were talking about, and it's just been a really exciting process to be part of the MIT team that got to work on these cameras and then hand them off to orbital and see how the spacecraft has come together over the course of development.
Yeah, that's a picture of the entire encapsulated fairing, the nose cone that sits up on the top of the launch vehicle. In that picture, that was sitting on the transporter waiting to go over to the pad. Additionally, after we launch, we will be doing the mission operations from our Dulles, Virginia Mission Operations Center throughout the entirety of the mission.
And who's got questions about the spacecraft? Lots of them. Wow. Okay. We're going to start here in the middle aisle, 3rd row here.
Okay, so I've been here on TESS since day one. George Ricker, the principal investigator, contacted us back in February of 2010 to find a spacecraft partner to propose a mission to NASA. So 8 years ago, we then went through the various steps of proposal, concept study, engineering design, procurement and manufacture of components, assembly, environmental test, and launch site support. So that's 8 years of very much hard labor, and as my wife likes to say, she's ready for that other woman TESS to be out of my life.
All right, next question over here.
For me? Oh, thank you. Yeah, I'm an engineer like you are. I write software. What type of software does it take to get something like TESS up in the air?
So there's a couple of computers on board TESS. There's a main avionics unit that runs the basic health, power control, attitude control, thermal control, communications with the ground. Then there's a data processing unit that MIT combined with the 4 cameras that does some of the data processing of the camera images on board. Both of those have real-time flight software running on them.
All right, we're going to go over here.
So I hate to be bleak, but is there a backup TESS?
You mean another observatory? I stand at the ready to build another one if someone pays me to do so.
All right, we're going to go over here.
For how powerful the lens are, it's really quite small. And was it constrained by kind of the size of the satellite, or is this really the optimal size that was developed for this technology? Yeah. So TESS was designed to be this very compact satellite, and that's why you see the 4 cameras are so tightly packed. And yes, it is like a 10 centimeter effectively is about how big across those lenses are. And they are wide angle lenses, so it is like a fish eye. And yes, a lot of engineering and optical engineering went into developing how to make these really wide angle lenses so compact to fit into this spacecraft bus that was designed to be very small.
All right, we've got time for one more question in the show, so we'll go in the back row here.
Hi guys, thank you for being here. So after the mission is over, we talked about how this might be extended, but as missions change and things change, could the optics, could the satellite be reconfigured, repurposed to maybe target a unexpected object that may enter the solar system, or even turned around to look at environmental science and picture different parts of the Earth?
This first. So the LeoStar 2 spacecraft bus that we produce is a fairly robust and agile platform. So we should be able to do almost anything the scientists dream up. We will wait until the extended mission portion to do that. On previous missions, scientists do come up with new ideas, and we work with them to look carefully at the engineering to see if that's possible. But yeah, there are very many other ideas that have been floated that we think are possible.
Yeah. All right, wonderful. Thank you for telling us a little about the spacecraft today. Wonderful. All right. So that leads us to the fact that we are out of time today talking about this here. For those who are watching on NASA TV, we have a pre-launch press conference coming up at 1 p.m. Eastern Time today, live on NASA television. If you'd like to follow along with the mission, though, on social media, you're welcome to. It's at NASA_TESS on Twitter or NASA TESS on Facebook. Going from there, you can also learn all about it by visiting NASA's website at www.nasa.gov/TESS. With that, we look forward to launching tomorrow evening at 6:32 p.m. Eastern Time from Space Launch Complex 40 here at the Cape Canaveral Air Force Station in Florida. And so with that, thank you very much for joining us today. Go TESS!